Hi, BC Calc. These are your day 72 notes. We're finally getting into the calculus of logs and exponentials. We are starting chapter 7. And to get the party started here, we're going to take a look at an accumulation function. So the accumulation function we're going to analyze to start getting an understanding of some calculus of logs is f of x equals the integral from 1 over x of f of t dt, where f of t is 1 over t. So if we think about the integral of 1 over t, that's something we don't know how to find the antiderivative of using our anti-power rule, because you get t to the negative first, and we add 1 to that, and then we get t to the 0. Dividing by 0 up front is going to be an issue. So we want to start building, well, what is the antiderivative of 1 over x? And we can think of it in terms of this accumulation function and have the calculator help us and assist us in this. So I'm going to recommend that you do at this point is hit pause real quick and create a sketch for f of t first, where t is greater than 0. So think about what 1 over t looks like just on the interval where t is a positive number. And then fill in this table in the middle. It says use a graphing calculator. So if you go to y equals on your calculator, type in your accumulation function here. And then to fill in the table, when x is 1, you're finding the integral from 1 to 1 of f of t dt, which you probably already know what that is over here. But then I want to go from 1 to 2 and 1 to 3 and 1 to 4. And then we're going to go backwards from 1 to 1/2 and 1 to 1/10. But set the window or set your table setup to ask. And you should be able to ask, hey, when x is 2, here's the value that you get from the accumulation function, 0.693. And what we know is that those outputs are on the function f of x. So we're inputting these values to the accumulation function. But the output is a y value on f of x. Then you're going to sketch that resulting graph over here. And in the end, be able to make some conclusions about the antiderivative of 1 over t. Okay. Go ahead and try that. I'm going to start showing you my answers. And hopefully in the end, we get something that matches here. So the first part was sketch f of t for t greater than 0. And so here's what you got. Right? It's that part of the hyperbola curve, 1 over x, just in the first quadrant. So then from there, kind of building our case for our table of values, it makes sense that the integral from 1 to 1 is going to be 0. I showed you the integral from 1 to 2 is 0.693. So that's going to be a point on the curve 2, 0.693. When you do the accumulation function from 1 to 3, you get 1.099 and then 1.386. So we get some y values that are slowly increasing over time here. And then maybe not too much of a surprise that when I integrate backwards from 1 to 1/2, that we get this negative accumulation. Negative 0.693 is the y value there. And then finally at 1/10, as we kind of get closer and closer to x equals 0, which would be bad anyway. We can't integrate at 0. We're going to get negative 2.303 there. So my resulting graph, after considering maybe our set of data points here, is something that looks like this. And maybe you're looking at that and saying, yeah, that looks pretty familiar to me. I hope it does. And for those of you that maybe already knew what the integral of 1 over x dx was prior to today's lesson, hopefully this graphical perspective helps you to justify that. But let's talk about some of the conclusions that we should make based on the properties we're seeing in our graph up there. There are 5 things that we're going to list. Number 1, it contains the point 1, 0. So we have an x-intercept at 1, 0. Number 2, as x goes to infinity, y goes to infinity. So thinking about a little bit of end behavior, we want to start thinking about what function models this that has and contains all these properties. Now, as x goes to 0 from the right, we get y is going to negative infinity. That definitely looks like we're approaching some sort of vertical asymptote. The graph is entirely concave down. That's a good way to describe it based on the inflection there. And then it is always increasing as well. So if we put all of these pieces together, what are we building towards? What function are we talking about? F of x? F of x is the natural log of x plus some constant c. Okay, anything of the form ln of x plus c would have these properties and can be defined by that accumulation function here. So therefore, if we check on the calculator, you can do y1 as your accumulation function, and y2, you can type in ln x. The only thing you have to be careful about when checking and confirming this on the calculator is when you go to set your window, because we know the domain of the natural log function is that x has to be positive. When you set your window, you don't want your accumulation function to start by testing negative x values. So maybe you want to make your x-min 0.1 or something like that. And that might be the only thing you have to change about the window, such that when you hit graph, it's going to start graphing your accumulation function slowly but surely. I'll bring this back up later. We'll see how close it looks to ln x, because then I'll graph ln x as well. Actually, you know what? I'm going to quit this for a second. Let's stop graphing that. Let me type in ln x at the same time. This way, it doesn't try and regraph that whole thing for me again. Okay. So hopefully in the end, the blue and the red graphs will be right on top of one another. I'll bring this back up in a few moments and we'll see how much longer it takes to graph the accumulation function there. Okay, so some really quick, hopefully graphical perspective as to how we can use this accumulation function to find the antiderivative of 1 over x, which we now know is ln of x. All right, so moving on from there, on the next page, we have some log properties. Log properties are going to be pretty important to us in this unit in terms of doing a few things. Finding derivatives of more complicated cases, using properties of the product, quotient, and power rules. Those will be all very useful to you. So, for example, ln of a times b, that's going to be ln of a plus the ln of b. So hopefully you remember these properties as far as multiplication expanding to addition. If you have ln of a over b, the quotient rule would be ln of a minus ln of b. And then finally, ln of x to the a power. The power property here brings the exponent to the front, so we get a times ln of x. And these rules, like I was saying, do help us to prove other cases later on. They'll help us in finding derivatives of exponential functions. They'll help you in finding derivatives of maybe things that aren't even exponential or logarithmic in nature. But you can use these properties still to find derivatives of pretty complicated looking functions later on. So this practice section, just to get some quick practice with the properties, it says rewrite each of the following in terms of ln2 and ln3. And the only one I'll do with you just to kind of get you in the mindset is let's do number 1, ln of 12. What you want to do for each of these examples is break the number on the inside down in terms of 2s and 3s so that you can eventually expand and write it in terms of 2s and 3s. Well, hopefully it's jumping out to you that 12 is 4 times 3 and 4 is nice because it's 2 squared. So you can write the inside here as 2 squared times 3. And then from there, you're going to go ahead and expand that using 2 of the properties above. We have exponents and we have multiplication. So this is 2 times the ln of 2 plus the natural log of 3. Okay, bring the exponent to the front of just ln2, and then multiplication expands to addition. So that's what each of these are going to start looking like as you expand. So see, they don't all have to have ln of 2 and ln of 3 in it, but those are the only 2 natural logs that I want each of these to be written in terms of. So go ahead and try those others. We'll go over them quickly next time we are in class with one another, but let's talk about a little bit more with the calculus of the natural log. We now have seen that the antiderivative of 1 over x dx, or 1 over t dt, according to this accumulation function, is ln of x. So if that's true, if you were to take the derivative of both sides with respect to x, we know that the derivative of ln of x is, well, according to the fundamental theorem, isn't that just 1 over x? So fundamental theorem gives us this rule that the derivative of the natural log function, therefore, is 1 over x. We're going to do some practice with this in a moment. Just as a quick generalization as well, the derivative with respect to x of some function ln of u would be, in general, 1 over u times the derivative of the inside with respect to x. So a little bit of a chain rule step here that we're going to do 1 over the quantity on the inside for our derivative times the derivative of the inside, as the chain rule implies. Okay, let's see if we can put that into practice on the next page. So it says find the derivative of each of the following. Y equals the ln of 5x cubed plus x. So the derivative dy dx would be 1 over the quantity 5x cubed plus x. And then we have to multiply by the derivative of the inside for that chain rule component. So that's going to be 15x squared plus 1. And there's not really a lot to do to simplify this here. You can write it as 15x squared plus 1 all over 5x cubed plus x. I guess if there was more to do with factoring and simplifying, we could do that here. But even though we could take out a GCF of x in the bottom, I don't think that's necessarily going to help us simplify any further. Okay. If I move on to the next two examples, you'll notice in the next two cases that we have absolute values surrounding the quantity within our natural log. So in theory, if you're finding the derivative of a quantity with absolute value, you should really split it up into two cases. Okay, one where the quantity on the inside is positive and one where the quantity on the inside is negative, and find the derivative of each. But what I'll tell you is for these cases, if you split the absolute value into those two cases I was just describing, one where the quantity on the inside is positive, one where we negate it, I'll tell you the derivatives are the same. So to save us some time, I'm not going to make us go through that process, but for these examples, we'll find that if we split it and go through the process of finding the derivative of each, we'll find that the two derivatives match. So therefore, when I find the derivative, we can just almost assume the case where x is positive and say the derivative of ln of absolute value x cubed plus x squared is 1 over x times the derivative 3x squared and then plus 2x. And that one we might be able to simplify a little bit further, right? Take out some GCFs of x there and simplify. But to be honest, I don't think we'll need to do that too much in our examples. Let's just move on to number 3 quickly here. The derivative would be 1 over sine x times the derivative of sine x, which is cosine x. And this one's pretty interesting because if I simplify and think of this as cos over sine, well, the derivative of ln of absolute value sine x is cos over sine, also known as cotangent. And the reason why I think this then becomes so interesting is that means that if I were to work backwards from here, that the antiderivative of cotangent, the antiderivative of cotangent is the ln of absolute value of sine x. This lesson, taking some antiderivatives, but you know what, while we're on the topic, let's talk about it. So we know that the anti-power rule works as long as n is not equal to -1. We've really avoided that case for a long time. Okay, clearly if n was -1, we're going to get this case where we have u to the 0 over 0, which is no good. But it's okay. Derivative of 1 over u du, that's just the ln of u plus c. But I'll tell you that this really only works in the case where u is a positive number. That's the only way this is defined for that natural log function. So what happens if u is negative, if u is less than 0? Well, if u is a negative number, what winds up being a result of finding the antiderivative is that you get ln of negative u plus natural log function. Sorry, I just saw that the internet might have cut out. Hopefully we're still here. So therefore, the antiderivative of 1 over u du really should be written as a piecewise, that it's ln of u plus c as long as u is positive, but if u is negative, it's technically ln of negative u plus c. So every time I write the antiderivative of 1 over u, do I want to have to break it up into these two cases? No. So how do we fix that? Well, it's the connection back to what I was talking about earlier at the top. Instead of writing this as u or negative u, depending on if u is positive or negative, what if we write it as ln, just absolute value of u, plus c? And that's what we have to list as our antiderivative of 1 over u du. Okay, so the absolute value is important here because we want to make sure that if u is negative, that we're still within the domain of this natural log function. Okay. Moving on from there, let's do a little bit of practice with antiderivatives on the last page of today's notes, and then we'll go from there. So when we look at this last page, I think using u substitutions is a great idea because we're looking for something of the form 1 over u du. So with whatever's in our denominator, if it's not in this exact form, let's see if we make that u. If du is just some scalar multiple of what we have up in the numerator here. So du in this case is just 1 dx, which is exactly what I have here. So I can turn this into 1 over u du. And then from there, if I find the antiderivative, we know that's ln absolute value of u plus c. And since u is x plus 1 for indefinite integrals, of course, we do have to replace x for u here. So ln absolute value of x plus 1 plus c is the antiderivative of 1 over x plus 1. Similarly, for number 2 here, same idea. Let u equal the denominator, 1 plus x squared, and notice how du is going to be a scalar multiple of x dx here, because this is just going to be 2x dx. So if we multiply both sides by a half, half of du would equal x dx. And I'm going to pull that 1/2 out front and take the integral of 1 over u du, which is ln absolute value of u. And since u is 1 plus x squared, we can go ahead and replace that with a plus c. You might actually see this example written as the following. You might see it as 1/2 ln of 1 plus x squared plus c without the absolute value. And the reason being is that the quantity 1 plus x squared, so the absolute value is a little redundant there because this is always positive. You can actually drop the absolute value in that case and just know that if this were a multiple choice question, we don't need the absolute value to make this statement true still. Sorry, I hope you guys are still with me. My internet keeps saying it's cutting out, but we'll see. All right, so we know that the antiderivative of 1 over x is ln absolute value of x. And you can see how the absolute value is super important when we find that antiderivative. Otherwise, when you plug in your bounds of -2 and for the lower bound and -1 for the upper bound, you're not going to be able to evaluate unless you have that absolute value. There would be no area under this curve if we don't have that absolute value there. So it's the ln of the absolute value of -1 minus ln absolute value -2 minus the ln of 2, which you can write of one of two ways. You can think of this as condensing the natural logs to division. We work backwards with our properties. Ln of 1 minus ln of 2 is the same as ln of a half, subtraction when condensed to division. Or ln of 1 is just 0. So since ln of 1 is 0, we get negative ln of 2 as our answer. Bringing it up as the exponent. 2 to the negative first is, in fact, 1/2. So if we think about what 1 over x looks like over this interval where the bounds are negative, it makes sense that in the end, this approximation will give you some negative accumulated area because of where that is in location to the x-axis here. Okay. 2 more that we have in the notes that we might as well do quickly here. If we look at number 4, we have ln x over x dx. So think about what our u is going to equal in this case. Maybe if I wrote it like this, it would be more obvious, ln x times 1 over x dx. Remember, the whole point of u substitution is to choose a u such that your du, the derivative of that term, is somewhere else within the integrand. And in this case, if you let u equal the ln of x, well, isn't du what's left there? 1 over x dx. So that's a little bit different comparing it to the ones that we saw, numbers 1 through 3. But if u is ln x, here's my du right here. So now it's the integral of u du, which is u squared over 2. And since u is ln x, we get ln x squared over 2. And don't forget about your plus c. Okay. What we're going to start becoming really accustomed to is getting used to looking for setting the the denominator to u because we're going to get some natural logs to appear from taking the integral. But if we try this one more time where we let u equal the denominator, does du have some connection to sine x dx in the numerator? Of course it does, right? So the derivative of 3 cosine x, my du would be -3 sine x dx. So if we multiply by a -1/3 out front, that would balance this such that we get the integral of 1/u du. Okay, so we get -1/3 ln the absolute value of u, which is 1 plus 3 cosine x with a plus c. And that is some really good solid practice with finding the antiderivative of quantities that result in natural logs in the end. So since I did all the examples in the notes, next time I see you in class, we'll do some more derivative and antiderivative practice with this new concept of having natural logs in our answers. Let me know if you have any questions about this. Hopefully this all recorded, because it looked like there were some internet issues. We'll see you guys next time.